All right, in this video we're going to be looking at gear ratios. And then we're going to use gears to change the speed of rotation, change the direction of rotation, or change the amount of torque going in and out. The variables that we'll be using, we'll use N for the number of teeth, D for diameter. We're going to use W for angular velocity, and actually we're going to use the Greek W that is the lowercase omega, and then the Greek T, which is tau, for torque. Alright, so if we've got two gears, or if we have idler gears between them, it doesn't matter. We're just looking at the in and out. So you've got the number of teeth, diameter, the RPM, and the torque. And so if we enter those values, we can set them all up as proportions. So if we look at the gear ratio proportions, number of teeth out divided by number of teeth in, diameter out divided by diameter in, RPM in over RPM out, torque out over torque in. You can see all of our units of measure cancel out. And we're left with 4 to 1. Okay, 32 divided by 8 is 4, 16 divided by 4 is 4, 40 divided by 10. So you can see all of these are actually the same fraction. So if we reduce the fractions, then that gives us our gear ratio. The one unit we need to look out for, it's a little bit different. They're all out over in, except for our RPMs. So if we've got the big wheel is going slower, or if the big wheel is going slow, the smaller wheel is going to be going faster than the big wheel. If the little wheel is the input, it's going to be turning faster than the output. So it's going to be inversely proportional to our other ratios. All right, so if we look at this, we've got the larger gear, the green gear is turning the small gear. So it's going to take more effort, but you'll get more speed. So it's like if you're on a bicycle and you want to go really fast, then you're going to have the chain on the biggest sprocket in the front and the smallest sprocket in the back. So going down hills on level ground, you can go really fast. Going uphill, it's going to take a lot of effort. So in that case, you would want to change it, especially if you're going up a really steep hill, where you're going to be on the smaller gear in the front and the biggest gear on the back. You're going to go slower, but it takes less effort. So if we look at this example, if we've got the green gear as our input, the green gear is the output, so we're pedaling on the smaller gear in this example. So our input gear has 14 teeth, our output has 70. We set them all up. And all of these are 5 to 1. 15 divided by 3 is 5. 70 divided by 14 is 5. 3 divided by 0.6, or 75 divided by 15. All right. So since we know that, we can do calculations as long as we've got one of our gear ratios, whether it's the number of teeth, diameter, torque, then we can figure all the others out. Now if we look at this one, looking at our gear ratios, if we compare A to B, that would be 18 over 10, which is 1.8 to 1. If we look at gears B to C, we get 14 divided by 18, which is actually 0.7 repeating. So I've rounded this off to 0.78. That's why I've got little squiggly lines right there instead of equal, because it doesn't actually equal, but it's really close to 0.78. And then if we look at C to D, that's 10 divided by 14. And again, I rounded this one off because it was a fairly long decimal, so it's approximately 0.71 to 1. So if we look at the total gear ratio, we can multiply all of those together, which comes out to 0.997 to 1. But again, I rounded off, so it's approximately 0.997 to 1. if I had not rounded off, we'd actually end up with a gear ratio of 1:1. Now, if A and D were connected directly to each other, 10 divided by 10 is 1:1. So what this shows, those gears that are in between, unless there's some friction in there that's slowing them down, or we've got some sort of power hooked to them so that they're helping out, all they're doing is just changing directions or giving us distance between our gears. There's a lot of different reasons we might want to put gears between them. But the idler gears really don't do anything. All they're doing is separating our gears or changing directions or something like that. So if we look at this gear setup, again, the gear ratio between A and B, we've got out over in, and on this setup we're looking at A is our input, C is our output. Okay, so we get gear ratio of 2:1. If we look at between B and C, 42 divided by 28 is actually 1.5:1. So if we look at the total gear train ratio, there's two ways we can do it. We can just look at the input gear and the output gear, which gives us 42 divided by 14, which is 3:1. Or if we multiply the gears together, 2 times 1.5 is 3. Again, we get 3:1. So it doesn't matter if we look at all of them or just our input and our output in this type of gear setup. All right, so if we look at the input torque, the input revolutions, and the input diameter, we can calculate the output because we know the number of teeth that we have in our input and our output. So we're going to be looking at our number of teeth and our torque. So we set up the number of teeth, that's number out over number in, torque out, what we're looking for, over torque in, which was 40. We cross multiply. 42 times 40 is 1,680. Then we've got 14 times our torque out. We divide both sides by 14, and we get 120 foot-pounds of torque coming out. So you see we've got the smaller gear driving the bigger gear, so we get a lot more torque going out. All right, now if we look at our revolutions per minute, our revolution should be slower since the little gear turns faster than the larger gear. So remember, this is the one that's inversely proportional, so this is the in going out. So we set up the 42 over 14 just like we did in the first one. And we've got 21 divided by our RPM going out. We cross multiply. We get 294 divided by 42. So our revolutions going out are 7 RPM. And then we can find the diameter of the output wheel. Same way, I know the input diameter is 8 inches. So we set up our two fractions. We cross multiply. 42 times 8 is 336. We divide by 14 and we get 24 inches. Now we can go with a little bit different gear setup. So we've got one like this where we've got A is driving B, then C is attached to B, and then C is driving D. So that B and C gear attached together, that's not just an idler gear. That's going to change our ratios. So if we look at the gear ratio between A and B, we get 28 divided by 14, which is 2:1. If we look at between C and D, it's the same thing. We've got 28 divided by 14, which is 2:1. But on this one, we can't just look at A and D and go, oh, okay, the output's 28 divided by 14 is 2 to 1. Because of that center gear, the way this is set up, we do have to multiply these together. So that'd be 2 over 1 times 2 over 1, which is going to give me a gear ratio of 4 to 1. All right, now if we look at this setup, we've got gear A is the input drive. It's attached to a motor that produces 30 foot-pounds of torque. What is the output torque? All right, so our ratios are still the same. We just look at what we have and what we need. Okay, we have the number of teeth in and out. We've got our input torque. We're looking for our output torque. So we set up our fraction. We cross multiply. 24 times 30 is 720. 16 times T out is just 16 T out. We divide by 16. And we get 45 foot-pounds of torque coming out. And again, we've got the smaller gear driving the bigger gear. So we're going to get more output torque than we've got going in. All right, let's look at one more. On this one, we've got the larger gear driving the smaller gear. And we've got the RPM of 40 going in. So we're looking at the revolutions per minute going out. So since we've got the larger gear going in, the smaller gear should be spinning faster if we do our calculations correctly. Again, we look at our ratios, we look at what we have and what we're looking for. Okay, so we've got the diameter in and diameter out, 6 inches and 22 inches, and we're looking for the torque. So we set up our two fractions, we cross multiply. 22 times 40 is 880. We divide both sides by 6. And we get 146 2/3 RPM.